today we're going to take a look at a few myths around LEDs. Now, this isn't a presentation that PhotonStar had written, but it really captured my imagination when I saw it in 2010. And the same kind of issues are still prevalent in the market, and customers still believe the same thing. So I guess what I thought we'd do is run through somebody else's presentation. This is by way of an entry level into LED basics. Okay. Okay, first myth, LED technology is new. Let's look at that, shall we? There's Thomas Edison, circa 1880. We all know what he did, invented the incandescent light bulb, or the first practical one. What's this? Henry Round produced an LED in 1907, which is a bit of a surprise, isn't it? I think the point, though, is that by that time, Thomas Edison had made significant commercial traction with the with his incandescent light. But the problem here was that the LED wasn't very efficient, and that continued for a long period of time. But it's not new. LEDs are not bright enough for lighting. I think we possibly have gone past this point, but let's just look at the evidence. There's some LED lamps. This is the US DOE roadmap. Now, this is the 2002 roadmap. If you go and type into US DOE into your internet browser, you'll be able to find lots and lots of LED roadmap information from the US DOE. There's some really good ones in there. It's been updated more recently, but we're still on track with this. So the 2020 target is 200 lumens per watt. Wow. Actually, we'll go on to talk about that in a bit, but we're now at 276 lumens in the lab, so this is why it's been updated. So we're actually progressing faster than was expected. Okay, this is another result from Cree in 2010, 200 lumens per watt. Actually, we're past that now at 276, and that was another February announcement. The third myth I guess I'd like to talk about is everybody thinks LEDs last forever. They last for hundreds of thousands of hours. This is not a myth, actually. If you test your LED properly, and you can get some data that will prove that you can make an LED last. So the method that everybody is using is an IES, which is North American standard, LM80. That's the basics of LED testing, and all LED packages and die are tested to LM80 standards. It doesn't strictly apply to luminaires, but the point is, if you've tested your LED to an LM80 standard, it's a really good start, because that means at least the basics won't, the LED won't fall over when put into a luminaire unless you've done something extremely bad to it. Okay, so they do last for quite a long period of time, but as you can see, there's LEDs grow old gracefully. So I guess what's defined usually is an L70 number, i.e. the LED will get 30% dimmer over a certain period of time, and that's generally what is quoted. But of course, if you get them too hot, this graph really just goes to show that the LED lifetime will drop dramatically if they overheat. So a good rule of thumb is to kind of ensure your LED junction temperature is around 85 degrees C or below. You can go a bit higher, and obviously LEDs are getting better and better all the time, but you know, if you keep to that rule, then you'll end up with a very solid, efficient product. Okay, so there's some more data showing that you can get that L70 number to be many hundreds of thousands. Now, these are obviously projected data, but as you can see, the harder you run the LED, the worse it gets. So overdriving LEDs, running them too hot, are things that are going to affect the lifetime in a negative way. So LEDs can last for hundreds of thousands of hours, but it depends what. Well, this is a fantastic thing from Bill Clinton. I like this when it came out, but it depends on what the meaning of the word is. The reality is there's got to be a lot of caveats around whether an LED is going to last a long period of time. So what are those? Are we talking here about an LED chip? Are we talking about packaged LED? Are we talking about a light engine? So you've really got to be specific about this, but generally, I guess what we would quote at PhotonStar would be LM80 data for the chip, and then we project into the IL-IG guide, which we'll go on to cover a little bit later, and we'll be looking at how that mapped into that. But LM80 data for a chip is a great start. LM80 data for a package is also a good start, and then it's down to what we do to it in a system. So I guess the point is you've got to be specific about what you're dealing with here. And again, this goes all the way through from modules, light bulbs, luminaires, etc. So let's take a light bulb example. Wow, there's a lot of components in there. And don't worry, don't expect any of you to get overexcited about what's inside the system. But I think there's a few components that generally represent weak links in here. So resistors pretty much don't mind getting hot, don't have any problems with that. Transistors, yeah, they'll overheat their semiconductors at some point. But the really risky ones are these guys here. The capacitor. And let's just highlight that. That little symbol there. They're in every single LED driver that's ever been made that I know of. And the reality of the situation is they don't like getting hot. Generally, if you put them in a light bulb, and here's an example, a couple of capacitors in there. The big ones, the big tube ones, are called electrolytic capacitors. They're the ones that generally don't like getting hot. Ceramic capacitors or thin film capacitors don't mind too much, but these ones, their lifetime can drop quicker than any other component in the system. Forget the LED. If you run these things at 100 degrees or 80 degrees, their lifetime can be thousands of hours and not hundreds of thousands of hours. So if you're designing a whole system here, you've got yourself a bit of a problem. So these are the bad guys, electrolytic capacitors. There are some good ones. It depends actually on who specified what when they build it. And the difference between a great LED driver for a lamp and a bad one is only about 60 cents. And the delta is usually the capacitors. And what happens there with a capacitor, you've got a couple of plates and you've got a gel between them. And if they get too hot and the capacitor hasn't been designed properly, or it's a cheap one in other words, the gel will dry out, capacitance will fall, and potentially, depending on how the circuit's designed, but the whole system can go live, so thus blowing up the LED. So that would be a bit of a bad thing. But they're the bad guys and the things to look out for. So I guess what we're talking about here is a manufacturing quality gap, i.e. has somebody specified something to last or not? Okay, so is it Christmas tree light quality? And I thought that's quite funny because we all expect Christmas tree lights to fall over constantly, or not? Or is it somebody that's made it properly or not? Or is it homemade? Somebody's put it on a hot plate, had to go. Is it, it really is about quality here. Some of this is about phosphors. Quality of phosphors is also important because this is another area that there could be a weak link. And if your chip has got LM80 data and you haven't got any LM80 data with the chip plus the phosphor, then potentially the phosphor might be the weak link here. The point being is, generally, if you stick with the main brands of quality LED makers, you're going to end up with good products, which is one of the risks, I guess, with some of the Asian import side of things. They may look good on day one, but may not last. Okay. The other area that I guess we all care about is it going to make the radio go weird? So has somebody actually put some effort into testing it? Is it marked properly? Is it approved? Has it been checked, etc.? So this is all really about manufacturing quality. And all of these things can make a big, big difference to the lifetime. Will somebody give a warranty on it? 30,000-hour warranty, 3-year warranty, 5-year warranty. At Photon Star and specification, we have a standard 5-year warranty because we have worked hard on all the bits. This is actually the guy who gave the presentation originally. I don't quite know what he was expecting to say about that, but anyway. Myth 4, all lighting class LEDs are equal. Well, I think you probably already know the answer to this. This is some data that was presented there, shows that some LEDs, and if you look here at these guys, this one here, that's a pretty solid LED. We've got the lumen number is fairly consistent over a fairly reasonable amount of time. So this graph runs to 30,000 hours. So clearly someone's put some effort into measuring that. That's a good LED. However, this guy here is starting off well, however, is dropping very, very quickly. So here, the L70 number is going to be about 3,000 hours, if you look, whereas the L70 number for this guy is probably going to be north of 30,000 hours. Okay, color shift is another challenge. Again, this is usually a symptom of overheating LEDs. So if an LED is cooked a bit harder than it should be, the junction temperature run too high, or the current is driven too high, the LEDs can shift in color. And in extreme cases, and this happened with some early, even Cree LEDs, you can get a situation where the phosphor will burn away and you end up with some black dust, literally. And I've seen this even recently with some downlighters that had Philips SLMs in them. And we tested these in-house at PhotonStar, and we only need to test them overnight to show that we could actually see phosphor burning and massive color shifts just by running the LEDs too hot. So this is happening even now, so it's not something that's behind us. Myth 5, there are no standards for lighting. Now, I think everybody kind of might think that, but the reality of the situation is there are a lot of standards. We'll come on to talk about it. This is just a few IEC standards. In the next presentation in the series, we're going to cover Selmer, Apples and Pears and standards organizations and just show you how many standards there are going on. And obviously what's pinning our LILG guide is a bunch of standards coming through Europe, because everybody's really trying to make sure that customers get what they think they are going to get. Okay, so there's safety standards, there's electrical performance standards, and there's just a plethora of them, and obviously we have access to all of these through the LIA membership, and we obviously design our fixtures at PhotonStar to comply with these, but not everybody does. So I think this really just goes on about the different sections here. I don't think we're going to dwell too much on this one. A number of people are not just trying to create standards, but they're trying to create acceptance criteria, performance criteria as well. So we've got the ECA, which is something we'll hear about, I think, in a little while, in another section of the Trusted Advisor training. We have the Energy Saving Trust, and of course we have good old building regulations which dictate efficiency levels, but clearly they don't dictate lifetime numbers. In summary, there are probably too many standards, but actually I think the situation is that a lot of these are now converging. Thus, actually, we're getting to a point now where the standards are starting to make sense. They're being developed by a lot of parties, but as I say, the IEC and other major standards bodies and ANSI represent the ones that are perhaps the most mature, perhaps the best thought through, and obviously they're the ones that are backing up the standards that PhotonStar and the performance measures that PhotonStar adopt. So this is a method from, I guess, 2000, and this is a discussion from 2010. So as a result, a lot of things have changed since then. Okay, so here we go. There's Forge Europa there with the government will look after LED lighting. Well, yeah, I don't think he is in the government, so he's not going to do it. I think we've got a similar photograph actually at PhotonStar with David Cameron, who actually then became Prime Minister having seen the light at PhotonStar. So anyway, we probably should just skip to the end of this presentation. I think we've got everything we can get out of that now. So anyway, we're going to pause at that point and move on to the next presentation.